right.
Okay.
Take it away, Laszlo.
And then we're back. Thank you. All right. So this talk is about building and using Python wheels. No surprise there. The horrors in the title comes from the experience you might see if you try to use incorrectly built or tagged extension wheels. And in this talk, I wanted to talk a little bit about some of the issues you might encounter. Some of these problems, diagnosing them can be quite horrific. It can be quite challenging. And I wanted to bring some real-world examples of these sort of issues and show you just some of the techniques, some of the challenges and the sort of tools the Python ecosystem gives you to overcome these problems. My name is Laszlo Kiss. I work at Bloomberg in the Python infrastructure team. We have about 6,000 developers in the company. Most of them, more than 4,000, uses Python in some capacity. And our team owns tools and workflows to support these Python engineers. In particular, one of the things we do, we own the Python application and library packaging and publishing workflows in the company. So this gives us a lot of experience with dealing with incorrectly built Python extensions and some of the issues users might come across. I'm also occasionally working on the audit wheel and manual Linux projects, which are specifically dealing with resolving the sort of issues and giving you tools to avoid these kind of problems. And so these projects also give me some experience and a lot of sort of user reports about just badly built stuff and how to deal with them. All of the examples in this talk I'm going to show you are actual real-world, incorrectly built and tagged and just like badly built wheels, which I've come across pretty much in every case as a user report, as a bug report that this is not working, investigating them. Okay, so let's start high level and talk about Python wheels. Who here knows what Python wheels are? Okay, cool. So I guess about half of the audience. And who knows what platform wheels are? Platform wheels? Okay, we'll cover it. A few people. So let's first take just an overview of what these things are, and then we can go into the weeds and look at all the problems you might encounter using them. So first, Python wheels, they are pre-built Python packages. Basically, you take a source distribution, the Python source code, and you take a build step, which can mean just simply copying the Python files into this wheel, which is a zip file with a special extension. Or it can also mean if you have extensions, modules which are written in some native language like C, C++, or Rust using the C API of CPython. In that case, you will have an actual build step compiling code and putting the results into the wheel. For users, Python wheels are great because when you're installing a wheel, you can completely sidestep the build step. At that point, someone has already built the wheel, all the contents of it. All you need to do, or the package installer like pip needs to do, is to take the wheel, unzip it, and put the contents in the right place. So it's much faster, it's much simpler, and you also don't need to have all these build tools installed in your environment. So wheels are great, and everyone should use them. There are two flavors of wheels. One is pure Python wheels, and the other is platform wheels. The difference can be easily sort of demonstrated by the contents. For the pure Python wheels, we have generally three different things in the wheel. We have Python files, obviously, and we have some data files optionally, data, configuration, pictures. These can also be packaged into the wheel. And then we'll have some metadata. The metadata describes what is inside the wheel, some properties of the wheel contents, which helps the package installer and other tools understand what's actually in the wheel. Platform wheels are very similar, and they can also contain these three things, but they will also contain native libraries. Native here means that these are specific to the platform, and this is also why these are called platform wheels. These native libraries can be two different things. They can be extensions, and these would be the compiled extensions which bind to the CPython C API. So you can write something like this in C, C++, your favorite language basically, compiled language. And what this gives you can leverage the CPython C API to build a Python module, which is not actually written in Python, but you can import such a module in the Python interpreter, and you can use it just as any other Python module. The great thing about these extensions is that because they can directly leverage the C API, they can be much faster, they have certain advantages over writing code in Python. One of the things about them is that they are platform specific. You cannot use these on any platform, and as we will see later. The other kind of native library you might see in these wheels is library dependencies. And those dependencies would be libraries, general purpose libraries, so not written in Python. They can be maybe written in C, and they implement something needed for this extension. It's a dependency. You might ask, if it's not written in Python and it's not actually part of that sort of Python package, then why is it in the wheel, right? And we'll see that later, why this makes sense. Here is a brief example of a pure Python wheel just for completeness. This is the Flask library, and you can see here the two kinds of data this contains. There's Python files, and there is the metadata, which is defined in specifications and explains to tools like pip what exactly is inside the wheel. Fairly simple stuff. And here we have a platform wheel. The platform wheel is a bit more complicated. This is NumPy in the example. And there are a lot of files here, and I actually had to trim the contents to fit on the slide. I don't know how visible this is on the projector, but I'll explain, bear with me. So again, we have metadata there in the middle in greenish. We have Python files at the bottom, simple stuff. And then we have this, I don't know how visible that is, but we have this Pocket FFT internal native extension. So this is a native extension which you can tell because first it ends with an SO extension, so it's a shared library object. And the second thing is you might notice that the file name contains things like CPython 3.11, 64-bit Linux, which makes this platform dependent. That's the only CPython version and platform where you're supposed to use this. You'll probably have a bad time if you try to use it on any other CPython or platform. And then, thirdly, on the top there, you see those three libraries, which are, again, platform-dependent libraries, but those are not extensions or Python libraries. Those are general-purpose dependencies, in this case, libg, Fortran, OpenBLAS, math libraries, which have been copied into the wheel. And also, there's something weird going on with the file names. You can tell there's some digits and letters in there. We'll come back to why this is happening, why this is done later. Okay, before we move any further into sort of the horrors, we have to understand the file name, because the file name for platform wheels gives us a lot of information, a lot of crucial information, and understanding them helps us to sort of better understand why these issues might happen. So in this case, zooming in on the file name, what we see here is pretty long file name. These are hyphen delimited wheel tags. So the wheel tags are specified in PEP 452. Yes, 452. These wheel tags standardize what exactly that wheel contains. So this tells us things like, and if we now split this up into the tags, you see that there are a few words here which we can decipher from the file name. And these are the wheel tags distribution, which is NumPy version 124.2. Python tag and ABI tag tell us what CPython version, in this case CPython version, this was built against and what ABI it requires. So basically it just tells you that you need CPython 3.11 for this wheel. And then the last one is the platform tag. The platform tag is the most interesting thing for us in here. And we're going to zoom in again. What this one says, Linux 217, Linux 2014. Let's take a look at this. The platform tag, as the name suggests, gives us the platform, where exactly this wheel is usable. In the good old days, this meant something like 32-bit Windows or 64-bit Linux. But as you might imagine, saying something like this wheel works on Linux 64-bit means it would literally have to support probably like 25 years of different Linux distributions, which is a lot. It's probably impossible. I should not say impossible because Pablo is going to prove me that I'm wrong. It would be very difficult to build a wheel which supports all of those platforms. So to better define this and narrow down sort of the Linux platform into something more manageable, something a wheel distributor can actually build against, the Linux standards were introduced. This started with Linux 1, and then 2 more were added. And we'll get into later how this has been evolving lately. But we're going to look at these first 3 for now. This is the original PAP 513, which introduced Linux. And basically what it says is that this is a platform tag for portable Linux build distributions. The idea behind Linux is that we can define a set of rules and standards, and if your Linux distribution complies with these rules, you can guarantee that the Linux, the wheels which use this Linux standard, they will work on that particular distribution. And this has been working quite well in practice. The core of this Linux specification can be boiled down to this snippet from the PAP itself. And these are the 3 main rules what it sets out. And this is the part in the presentation where we're going to actually stop with the boring stuff and actually get into the examples and look at these horrible errors just to understand what these mean. So we're going to look at some wheels which violate these standards. Okay, so the first one is that wheels should only depend on extremely limited set of external shared libraries. So to understand what this means, we're going to look at our first example. These are actual wheels in the examples which live on PyPI, but I removed the names just to protect the innocent. But this might be stuff you might actually come across in real life. So this one here is a dependency on an external library. So what happens here, we use Python 3.8, we install this example package, we get a many Linux platform supported wheel, everything's good. And then we try to use it, and it blows up in our face with this error message, which I think can be pretty confusing. It says that cannot open shared library object file, no such file directory. And then the maintainers actually took the sort of length to actually handle this error and give you a documentation link and say, this is what you do with something called LD library path. I think this is not great, because as a user, you are trying to solve a problem. Now you have a whole set of other problems to solve, right? So not great. What happens here is to demonstrate. We have our example wheel, that big box, and then we have a bunch of Python files in there. Those Python files, you will import one of those, and that will, in turn, import the extension itself. That's another shared object. And that shared object has some external dependencies. They are external because they are not part of the wheel. They are supposed to be on the operating system, installed somewhere. But in this case, they are not. Because nothing guarantees when you install this wheel that that external dependency should also be installed. It's not a Python package, so pip cannot really ensure that that is installed. And this is where the error happens. So this is bad because, first of all, this increases the complexity for the user. Now they need to understand that this particular wheel can only be used in this certain way. They have to figure out how to actually satisfy this requirement, install this other package, figure out how to actually install packages in their environment with the OS package manager and all that. But second of all, an even bigger problem is that even if you solve this problem and you install that external dependency, you cannot guarantee that that version of the dependency will actually work with the extension. Because whatever ABI, the application binary interface, your extension was built against, might not match whatever that dependency gives you. This means in practice that maybe your extension requires a symbol which was only introduced in a later version of the dependency, not the one you have at the machine. So again, this can cause issues. So to resolve this, the simple thing we can do is just to move this dependency inside the wheel. Once we move it into the wheel, users don't have to know anymore that this wheel is special in any way. They have to install anything for it to make it work. They just install the wheel, and everything works. The dependency is present. Except it's not that simple. And here comes another example. This is a small snippet from the contents of a different wheel. They tried to do the right thing here. And as you can see from the directory listing, this is a vendor sort of, and private. You're not supposed to look here. I don't know. Like this is a vendored libraries. So they basically copied what you can see here is the Kerberos and related libraries into the wheel. So these are external dependencies. They copied inside. They also resolved symlinks. That's why there are a copy of everything twice, but that's, I guess, fine. But the problem here is that if any of these libraries, for example, libkrb5so, if any of these is a dependency of a completely different extension, because of the way the dynamic linker works on Linux, there's only a single namespace. If an extension requires libkrb5so, the dynamic loader will link and load this one, this version, and any other extension which later also requires that library will get to use the same one. They will not be able to load their own version of it. And this means that we are back to the same ABI incompatibility issue. Now multiple extensions will have to share the same copy of that libkrb5so. And again, if you have a different version than what the extension requires, that's going to blow up, and that's not going to work. To solve this problem, what we can do is we can make this dependency unique. And we can make it unique by basically just renaming it to something fairly unique. You can take a hash of the file contents or something like that. But besides that, you also have to change all the references. So for example, here, the extension has to change a reference internally in the elf header called the needed section has to be updated and reflect the new name. Once we do all this, we are basically guaranteeing that nothing else can depend on this because it's unique to our wheel. And multiple versions can coexist in the same process space. If we go back to the NumPy example, you can actually see this exact process was applied here, where you see that all those Fortran libraries and OpenBlast, so they got moved into the wheel, and now, because they have a unique file name, nothing else should depend on it. So they're doing the right thing here, and the user doesn't even know that they need these libraries. Cool, so going back to the rules, this sort of explains to us that having a dependency on external shared libraries is bad. But what it says is that we should have only on an extremely limited set, not none, but an extremely limited set. And that extremely limited set is defined by the Linux specification. These are libraries which are okay to have dependencies on, and that's because they have extremely strong ABI guarantees. They don't tend to change. They are also very commonly available in Linux distributions. This list has changed, and it actually changes in different Linux versions. But this just gives you and tools a way to say, if your extension depends on any of these, that's fine. That will be available on the machine. But if you need anything else, you need to perform this vendoring step and move those external dependencies into the wheel. Okay, now we can move on to the second one. What this says is that Python wheels should depend only on old symbol versions in these external shell libraries. Again, let's demonstrate it with an example. So here, we see an incorrectly tagged wheel. Now we learned about the Linux standards, and we're going to see how it can be misused or abused. So in this case, we're running on CentOS 6, and then we install our example with Python 3.9. And indeed, we get a Linux 1 wheel. And as I foreshadowed now, it is not the correct Linux tag, as we will see. When we try to use it, we get this very impressive stack trees. I even had to trim to fit on the slide. At the end, it basically just says that glibc 2.14, this particular symbol version in libc cannot be found. What does this mean? So now if we look at the different Linux versions, we can see here that the first three, what I mentioned so far, they all correspond to one major version of CentOS or Red Hat Enterprise Linux. So Linux 1 started with CentOS 5 and moved to 6 and 7. Besides that, they also correspond to a particular version of libc, the C standard library. And because of this pattern, someone actually introduced the perennial Linux standard, which we use now in more modern times, which just says that whatever version of libc you are requiring in this Linux standard, that becomes the version of Linux. So now we have Linux XY, where XY is just a libc version. So we can go back and actually relabel the old Linux standards and have aliases. And this means that, for example, now you can see Linux 2.5 or 2.12. So now when you see a Linux file name, now you'll be able to tell what libc version your Linux distribution needs to have minimum to be able to run these. Okay, so now with this knowledge armed, we can go back to that wheel to understand what exactly that error message was telling us. And indeed, if we go back and we use this cool tool called audit wheel, this can actually tell us a lot more information about this wheel. So we run it, and it tells us, one, that indeed it is using glibc 2.14, which is not Linux 1. And indeed, it also tells us that this means that this is a Linux 2.17 wheel. That is the minimum compliant Linux standard we can apply on this particular wheel. So if you go back here, you can see that, yes, Linux 1 or 2.5 can go up to glibc 2.5, which is not the case here. If it needs glibc 2.14, that must be at least CentOS 7, because that contains, it's the first one to contain symbols for this particular version. So in this case, the fix would be simply to relabel that wheel and put the Linux 2.17 tag on that. And that would ensure that people only install it on more modern operating systems which actually have glibc 2.17, and it will work there. Okay, so now we covered the two hard ones, and the last one is an easy one, because that just says that the wheels should only depend on a widely compatible kernel ABI, and that's basically never a problem because the Linux kernel is the most stable ABI ever, and they never change it, so we don't even have to cover it. That's just not a concern in general. Okay, now to sum all this up, what do we need to do to get a good working platform wheel? We need to only depend on old symbol versions. So this means that we need to build the wheel on the lowest supported Linux version, what we actually want to support. It also means that we need to do this vendoring dance, basically. We need to minimize the external shared library dependencies. So moving the external dependencies into the wheel, renaming them, updating references. And on top of that, we also need to apply the correct tags. And you might say this is a lot of work for library maintainers to do every single time they do a release. They have to make sure all this is actually in place. And yes, there are tools to help us. And that's what we're going to talk about now. So the first tool I want to cover is audit wheel. We've seen this one earlier. And besides just showing information about the Linux compliance of a wheel, it can also repair wheels. And the repair process is very useful if you want to distribute platform wheels. When you build a wheel, the build process will give you something which is not Linux tagged in any way. It's just going to say something in general like Linux 64-bit or something like that. If you run audit wheel repair, that will not just apply the correct tag, which you can specify as a flag, but it will also perform the vendoring step, and it will ensure that external dependencies will be copied into the wheel, and every reference will be correctly updated. Okay, so now we have a way to properly tag these wheels and prepare them, but we also need a way to build them in the first place to actually make sure that, as we said, we need to build in the minimum supported Linux version to be able to support that particular Linux. For this, we have the Linux container images. These container images support the corresponding Linux version. So we have a list here. It's pretty extensive, and this is actually not all. If, let's say you want to support Melon Linux 2014, which is CentOS 7, or similar distributions, and then you can pick that container image for whatever architectures you want to support, build your extension in that. It will contain all the tools, compilers, audit wheel, all the other tools you might need. And the output will be indeed Melon Linux compliant. It will ensure that you're only using symbols from that particular Melon Linux version. Okay, and if you say at this point that it's cool that there are tools, but you still need to actually plug these together and make sure that they work in your release process, that's where CI build wheel comes in, which takes all this and it lets you plug all this into your favorite CI solution. So for example, GitHub Actions or Azure Pipelines, and gives you a fairly simple way to basically just script this. It will take the correct Melon Linux or Muscle Linux images, which is another standard for Alpine Linux and other muscle-based libc distributions. And it will also correctly tag the wheels. For example, Linux, it will use audit wheel, but it would use other similar tools in other distributions. There is a nice matrix here of all the supported versions of Linux and distributions and platforms. And yes, Python 3.12 is missing because I forgot to update the slide, but that's also supported here. And you can see it's pretty extensive. So to sum all this up, I think we can say that building platform wheels is complicated, and getting it right is non-trivial. And if you take just one thing away from this talk, I think it should be that you should just adopt CI build wheel. Or if you're a user and you encounter some similar issues, you can just probably try to suggest to your maintainers that maybe you should adopt a CI build wheel. There's one more thing I wanted to say here, which is that we are hiring, and there is going to be an event just next week in Madrid on the 10th of October. This is mainly for entry-level software engineers. If you're interested, check out the QR code. You can see some details there. And there's also a URL. Or come and chat with me or one of my colleagues. I'm going to leave this slide up just in case anyone wants to take pictures. But that's it, and thank you very much.
Thank you, Laszlo. That was amazing. All right, so next up we have a round of questions. Anyone has a question, please raise your hand. Okay, we have a few of them. First over here.
Hi. Not sure if I understood it correctly, but is it that the many Linux version is always backwards compatible? Is that true or not?
Yes. So Melon Linux standards, if you take, for example, Melon Linux 1, it's forward compatible. So any distribution which is newer than Melon Linux 1 and is Melon Linux compliant, 2010, 2014, and so forth, the Melon Linux 1 wheels will work there. It's not backwards compatible in the sense that if you use something which has Melon Linux 2014 tag, you will not be able to make that work on Melon Linux 2010 or Melon Linux 1 compliant distributions.
But newer standards will always support
exactly.
the old ones.
Exactly.
But is there any, is it foreseen that this might, some standard might be deprecated at some time for not having to?
Sorry, can you repeat the question?
Yeah, the point is one can imagine that maybe this cannot be maintained forever.
Oh, right. That's a very good point. Yes, absolutely. And this can absolutely, in theory, happen. So one of the things, the first three Melon Linux standards, as they followed basically the Red Hat Enterprise Linux releases, so 5, 6, and 7, that was mostly based on the guarantees Red Hat Enterprise Linux provided, because of the core libraries, as I mentioned, which are okay to depend on. Those actually had a 3 major version forward compatibility guarantee. So that meant that Melon Linux 1 would at least be forward compatible with 3 major versions of those distributions. And this was pretty widely sort of copied in other distributions as well. They tend to be fairly consistent. But you might say, but that's only 3 major versions, and what happens at the 4th and the 5th versions, right? And the versioning also changed, and Melon Linux doesn't use, I mean, CentOS as a thing is not really a thing anymore, right? So that also complicates matters. And so we know that Red Hat is putting significant effort into making sure that this forward compatibility still remains. They cannot guarantee it, but there is still a strong sort of unspoken guarantee that this should work. libc is also very, it has a very strong ABI compatibility story. So in practice, it hasn't been an issue. But yes, this is actually a danger which the Python ecosystem might have to work around in the future.
But for now, for now is not any mechanism in coming, let's say.
No, there has been. This is actually something I've proposed in the past, that we might want to actually have something formal and automated to actually check these. But this requires volunteer time and actually someone implementing this. And it's a pretty complicated check to perform and expensive because of the combinations of things you need to check. But yes, it's a very good point. This is something we should have. It would be great to have, yes. Otherwise, we basically rely on the community reporting such issues.
Hello, very nice talk. I was just wondering if I saw your last slide correctly. I saw 2 versions for a Mac OS wheel, 3 versions for a Windows wheel, 32 and 64 bits, plus ARM, and then for Linux is a bunch of versions, right?
So there is basically the matrix goes. So on Windows, you have 64 32-bit and ARM 64-bit. On Linux, you have 64-bit Intel 32-bit, that's i686, ARM PowerPC S3990X, that's IBM. I don't know if anyone uses that.
But a part of what I see for the Linux columns would be many Linux 2.6, many Linux. So there are many Linux versions than.
Yes, this actually explodes into even more on Linux. There are even more combinations because for each pair you will have multiple many Linux versions. Yes.
So why is this situation so dire with Linux?
So the situation with Linux is that commercial operating systems like Windows and macOS you can basically just look at the fact that there is only one version, one sort of flavor. There is Windows, which releases updates occasionally, and there's macOS. But with Linux, we have lots and lots of flavors and distributions which have their own mixture of components. They might ship different libc versions, they might ship different other sort of dependencies. And that just means that you don't have that sort of release scheme. This where you could say that, okay, the next Linux version is going to be this. This is what it consists. There are many flavors. And this is what Linux tries to achieve. It's just that you have even restricting it to Linux, you have a more frequent release cadence. As basically now, where we are, every single time, technically every single time you get a libc release, you would have a new Linux standard.
Okay. Thank you.
I think there was a question over here.
So I guess, okay, so the most popular or the common repository where people download their wheels, voluntary or not, is PyPy. As I don't build wheels because it's not my work, but usually first is the developer or the project manager or whatever the one that has to do all that matrix of building different wheels. So it's not on the PyPy side, isn't it?
No, PyPy does not take care of building. It's just a repository for hosting the artifacts. So typically, if you're using GitHub, for example, you would have your source code there and you would have your build process maybe on GitHub Actions, which would actually perform the build there and just upload the artifacts to PyPy.
So as a user, probably like building on the other previous question, as a user, I don't know, there are packages like NumPy that thankfully right now have like lots of different wheels that they didn't have in the past. So if we use like different platforms or on our computers or maybe on the cloud or different, I don't know, Muscle, Alpine Linux, whatever versions, and we as users for deploying or maybe for helping to build all those different wheels, there are any, I don't know, resources, advice or whatever that would be useful to have a bigger pool of wheels there.
Right, you would like to cover as many platforms and targets as possible, right? If I understand correctly. So I think the best guidance there is just to look at the CI build wheel documentation and adopt that. The way it works is that you need a CI system, something it supports. And then you just basically declare that these are the platforms I want to support. You still need to make sure that your Python package actually builds correctly and works correctly on, I don't know, Windows or macOS or whatever platform you support. But CI build wheel will ensure that the entire build process is invoked in the right environment, you get the correct wheel tags applied, and those wheels are actually usable. So in terms of resources on the details on doing this, I think the PyPA has some documentation on building wheels, but it's not really sort of extensive in the sense that this is how we do things on this platform or on that platform. That unfortunately remains to be, something you can handle partly with CI build and partly you'll have to sort of debug these issues. Why is my wheel not behaving as it should on macOS, for example? And sometimes you just run into platform-specific issues, right? But I think that's a different category of issues.
Right, I think we are up. There's no time for more questions. So as always, if you have any other questions, please, I'm sure that Laszlo will be happy to answer them if you see him around off the record. So once again, please give him a big applause to Laszlo. Thank you for your talk.
Thank you.